Hey, welcome back. This is 2.6 in differential equations. Now we're looking at a numerical method for finding solutions. And what I'm going to do is kind of go through the exploration like they do in the book, but I'm going to use an easier differential equation. Okay, so this is kind of their tangent line approximation method, which is Euler's method. So let's consider this initial value problem. Let's consider this IVP. We have, in my case, y prime equals plain old 2x. So it can be a multivariable expression. And you see over here on the right, their expression a lot more complicated. 0.1 squared root y plus 0.4 x squared is a little more complicated. But for introduction purposes, I'm just going to use this. Okay, so y prime is 2x and y of 1 is 1. We wish to find y of 1.5. Okay. First, consider the direction field. Okay, so consider the direction field for this guy. And at all these points in the xy plane, you should have, we can produce a little tick mark to represent the slope of the tangent line to the curve at that particular point. So at 0, it's 0. At 1, it's 0. At -1, it's 0. At the point 1, it'll be then 2, right? So we should have here at 1, 2, the slope will be 2, so up 1, 2 over 1, so kind of tilted that like that. And then similarly here and here as well, because it's only dependent on your x value, not y. Okay, so if we start at 1, 1, what we're going to do is kind of plot our point here, and then we use this little tangent line. We're going to create the equation of a line and then use this to get to the next point. Okay, we'll have a fixed change in x value, which they're going to also call h value, but it's this tangent line that we're going to get a formula for, and then we use it to kind of get to our next position. And then we recalibrate with a new kind of tangent line, build a new tangent line, move over by this x value, and then recalibrate. So it's kind of like the way I usually introduce it in Calc 2 is kind of like the Spider-Man method. So you're starting at some point up here at the right in the xy plane, and it has a little tangent line, so you use that to get to your next point. And these points are always some h value apart in the x direction. Okay. And you're sort of at this point, you recalibrate with the differential equation and you produce a new tangent line, and then you use that to get to your next point. Then you recalibrate. So it's like at every point you're shooting like a web in the direction of the tangent line, and use that to get your next point. And overall, what you get is kind of a polygonal approximation to the solution curve. All right, so the solution curve will probably be a little bit more smooth, right? Maybe something like that. The farther you go and in your x direction, probably the worse your approximation will be. But anyways, let's carry on, right? Okay, so at this point 1, 1, we can approximate the solution curve with a tangent line. Okay, so at the point 1, 1, we can approximate the solution curve with a tangent line. To create the equation of a tangent line, we need two things, right? We need a slope and we need a point. M for slope. Okay. We already have the point. The slope, we use the differential equation, the y prime equals 2x. Okay. And in the book, they're calling that equation f of xy. Okay. So the slope, we have our f of xy, in this case is 2x. At this point 1, 1, then we could evaluate that to just be 2. So our tangent line equation, from the equation y minus y1 equals m times x minus x1, we just plug the material in, and we get y minus 1 equals 2 times x minus 1. And then you could rearrange things, and you have your equation of that tangent line. So this would be, 2x minus 2, and then add 1 to the other side. So y equals 2x minus 1. Okay? Okay, so I have this, I have an equation of a tangent line at this point. I can extend it in the xy plane here to whatever my next x value is, however far away I choose. Usually you don't want to choose another x value to be too far away. I'm going to go 0.1. I'm going to move my x value by 0.1. Okay, so anyways, basically I want to build towards this value y of 1.5. Okay, so this x value is 1.5. So I will move by some h value that is usually given by the problem, which is also, you could think of it as change in x. And in this case, I'm going to go by 0.1. Okay. So we have then my x sub 0, that's where I started, that was 1, that's given. So I'm starting at the 0.11. And then I move by this 0.1 to my new x value. So my new x value is basically 1 plus 0.1, so 1.1. And my new y value, I'm using this equation that I built in order to produce it. Okay, so y1 will equal 2 times the previous x value, which is 1. Or actually, I want to use my my new x value. So 2 times 1.1 minus 1 equals 2.2 minus 1, which will equal 2.2 minus 1 is just 1.2. Okay. Okay. Once I get to this new point here, this 1.1 comma 1.2, I create another equation of a line built off the differential equation, and then I could create another point. Okay, so what? Now I construct another tangent line at my new location, which is now 1.1 comma 1.2. So, again, I need a slope, and I can find that from the f of xy formula, which is 2x. So this time the slope will be 1.1 comma 1.2. I don't need the 1.2, it'll just be 2.2. Okay. And then my point is given here is just 1.1 comma 1.2, new point. And my equation from y minus y1 equals m times x minus x1. I go y minus 1.2 equals 2.2 times x minus, 1.1. And that will, from there I can form my new equation, right? So y minus 1.2 equals 2.2x minus 2.42, and then move the 1.2 over, so I get 2.2x minus 1.22. Okay. Okay, so now I get my new point. So from this, I get my third point. So my new x what number I'm on, x sub 1, x sub 2 is going to be 1.2, and then I can plug that into my new equation for y sub 2. So that's going to be 2.2 times 1.2 minus 1.22, which will equal 1.42. Okay? And you keep on doing this process over and over, and you can produce what is a general formula. Okay, so in general, for a new location, x sub n comma y sub n, the formula will be, so x sub n plus 1 equals x sub n plus h, and then your new y sub n plus 1, will equal your f of x sub n comma y sub n times x sub n plus h minus x sub n plus the y sub n. Okay? And of course, in here, you're going to see some cancellation. So the formulas will be x sub n plus 1 equals x sub n plus h. And then your y sub n plus 1 will be, if we rewrite it a bit, y sub n plus just plain old h, because these cancel, times f of x sub n, y sub n. Okay, right. So if we then use this formula rather than keep on creating a new equation of the tangent line, our x sub 3 will be 1.3 now, and then y sub 3 will be y sub 2, which is 1.42, plus h, which is 0.1, times f of x sub n, y sub n, comma y sub n. In other words, 2 times the previous x value, which in this case was 1.2. Okay. And then we could go ahead and evaluate and get a new y sub 3, which is 1.66. And then x sub 4 is 1.4, so y sub 4 will be 1.66 plus 0.1 times 2 times 1.3, which will end up being 1.92. And then x sub 5, which is the x value that we originally want, right? Because we were looking for y of 1.5. If you kind of remember, we wish to find y of 1.5. Okay. So x sub 5, 1.5, y sub 5 will be the answer we want. So y sub 5 is going to be 1.92 plus 0.1 times 2 times the previous x, 1.4, and that will equal 2.2. Okay. So, or thus, we believe y of 1.5 equals 2.2. We know the answer, right? The solution to that differential equation, the simple one that I started with, this differential equation here, the solution is x squared plus some constant c. We could use the initial condition to get that constant c. So plugging in 1 for y, and then plugging in 1 for x. 1 squared is 1. So c would be 0. So our solution is actually y equals x squared. We can compare this approximation with the actual solution. Okay? So we note the actual solution. Y equals x squared. So y of 1.5 should be 2.25. It's just 1.5 squared, right? So it's pretty close. In other words, it's kind of close. The two things that we need to work with for our answers in WebAssign would be absolute error and relative error. So in this last step, if x5 we found is 1.5, of course, y sub 5, our approximation was 2.2, the absolute error is going to be the actual answer, which was 2.25 minus our approximation. Okay, so the absolute value of it. So in this case, it's 0.05. And then the percent relative error, which we also will need for our work, is going to be the absolute error, 2.25 minus 2.2, absolute value all over 2.25. Okay, so, and then in this case, that will be approximately 0.02. If they want it as a percent, so it's 2%. Okay. Let's kind of look at maybe one of the homework problems here then. You probably don't want to do too many of these by hand. I mean, you can, but it can get annoying after a while. You just try a couple by hand and then go to like a computer to do it for you. So let's use this in this first problem. We'll do it one by hand, and then kind of I'll show you some calculators. Okay, so our f of xy, our differential equation, in this case is the 2x minus 3y plus 1. Our starting place is going to be 1, 7. And we're trying to figure out what y of 1.2 is. Okay. At first, they want you to try h equals 0.1, and then they want you to try h equals 0.05. So I'll do the 0.1. Right. So x sub 0 is going to be 1. Y sub 0 is going to be 7. X sub 1, add in 0.1, so you get 1.1. Y sub 1 is going to be the previous y value, 7, plus h, which is 0.1, times f of x evaluated at 1, 7. Okay? So I'm plugging in 1 for x, and then 7 for y. Okay. And for some reason, it's okay. There we go. You could. I'm just going to go to Wolfram and have, well, Wolfram is sketchy now because it doesn't give me enough decimal places like I want. So I'm just going to go to my calculator, if you don't mind, and evaluate it that way. Okay. So I'm in my calculator, 7 plus 0.1 times 2 minus 21 plus 1. So my first one is apparently 5.2. And then x sub 2 is 1.2. So y sub 2, which should be the answer we want, 5.2 plus 0.1 times 2 times the previous x, which is 1.1, minus 3 times the previous y, which is 5.2, plus 1. So let's see, 2 plus 0.1 times 2 times 1.1 minus 3 times 5.2 plus 1. In parentheses, I'm getting 3.96. Let's see if that's what I got earlier. Yeah, so 3.96 there. Then for the other one, you have to go by 0.05. So your x sub 0 should be 1. Your x sub 1 will be 1.05. And it looks like you're going to have to go all the way. You know, it's x sub 2 is 1.1, x sub 3, 1.15, and then x sub 4 should give you the 1.2 that we're after. Okay, so I'll do this one as well. So y sub 0, of course, I believe is 7. Y sub 1 will be 7 plus our new h value, 0.05 times 2 times 1 minus 3 times 7 plus 1. 7 plus 0.05 times 2 minus 21 plus 1. So it's 6.1 here. Y sub 2 will be 6.1 plus 0.05 times 2 times 1.05 minus 3 times 6.1 plus 1. Getting 5.34. Y sub 3 is 5.34 plus 0.05 times 2 times 1.1 minus 3 times 5.34 plus 1. .699, and then y sub 4 is going to be 4.699 plus 0.05 times 2 times 1.15 minus 3 times 4.699 plus 1. Getting 4.1592 if I rounded. I have no idea what they're doing for their rounding. So if you have an issue with this, send me an email like it's not rounding correctly. Because it should be, if you round the 4 decimals, it should be 4.191592. You can't imagine which universe you're in. So maybe they have, I don't even know what they could have done to get that answer. It's wrong. Unless, they've created some new way to round numbers. They're not rounding up. Because my answer is 4.15915. And what universe is that not going to round to 4.1592? But when I put that in for an answer, I don't think it'll mark it right. See, it marks it wrong. So there are some issues here. Just be aware of it. Don't flip out on me. You can send me an email, and literally I can go in and check and make sure you're on the right track, or even give you some helpful hints. And the second problem, you're going to have to do that absolute and percent relative error thing. You can, go after an Euler calculator. Usually I just go to the Planet Calc calculator. So if you Google Planet Calc Euler method, let's see what, yeah, they already have it set it up. So it's the same problem. We want step size for the first one, 0.1. Of course, the x, you could even set your decimals to 4. We'll set it to 5. And then calculate, and it gives you the whole table. It doesn't give you the absolute error, the percent relative error. You're going to have to chug that out by hand if you use this calculator. So anyways, you can see the answers right here all the way up to 2.5937. So this works pretty well. And then, like I said, you're going to have to get the absolute error and the percent relative error. So just note then, to get the absolute error, it's going to be the difference of your predicted value, in this case, minus the actual value, and you're doing the absolute value of that. Okay. So in that case, it's 937 minus 2.783, of course. 0.2124. Do I have to do this by hand? 5, I guess. My calculator is saying 6. I think I might have my calculator rounded weirdly, but I'm getting 0.1246. Notice I get 0.1245. 2.7183. 6, right? Am I an idiot? What's going on here? 246. Somehow I got 0.1245. Let's see if they said 1.246. Yeah, so they give you a little bit of leeway with your answer. Then the percent relative error, so that's going to be the difference between your approximation, 2.5937 minus 2.7183, divided by, what was it, the actual number, so 2.7183. And then I believe you have to multiply it by 100. So let's see. Divided by 2.7183. And then, yeah, multiply by 100. Or multiply by 100. Well, this thing is 0.0458. 458 something. Okay, and if you multiply it by 100, you'll get the 4.58, whatever their approximation is. So you're going to have to finagle that. Like I said, if you're getting your approximations are way off or something, let me know. You can code all of this Euler method stuff if you want to. You can go to like Python, a Python compiler. So Jupyter is like free now. So you can go in here if you get really ambitious. And the only problem with this is I haven't really figured out how the heck they are approximating inside of Python. I'm not that familiar with it, so. But I do have code for it. You can make up your own code, or you can ask me for the code. Like I said, the approximations kind of. Let me find the code I had. Python. You can code it to figure out your absolute error and that stuff as well. So if you just go to File, New, Python 3. We'll do that in and then hit run. It'll do the work for you. So the way I got it set up is this should give you the chart. But if you look at my answers, they're a little off. You know, as you get down farther and farther, a little off. So actually, this is the 0.05 version that I did here. I think I went a little bit too far. 2.6536. No, I got it. It's right there. And then 0.0647. Yeah, and then 2.38. Yeah, so it accepted my answer. I did 4 decimals. So if you want the code for that, you can kind of copy it down right now, or you can send me an email if you're ambitious enough and you're into computers. It's almost like computers, and you got it. If you want to make it in the real world these days, you got to know how to program. So that's my opinion. But, okay, so I guess we'll leave it at that. We need to do a video quiz. So let's make the last one the video quiz. We'll sort of do that one and maybe use Python here. So they say use a numerical solver and Euler's method to obtain a 4 decimal approximation using h equals 0.05. So I'm doing problem number 5. Y prime is xy squared minus y all over x. Y of 1 equals 1. And then they want to know what is y of 1.5. So I'm going to do mine in Python. You can use the Planet Calc if you want to. So x is actually 1 in this case. Y is 1. I want to do h 0.5. And go all the way up to 1.5. And I don't need that junk. I need to write in my formula. So in this case, it's going to be y plus h times f of x. So it's x times y. For exponent, you do a star star. This language minus y divided by x. And I'm going to go to 4 decimals. And hope it's times. Let's run it. Ooh, didn't like it. For some reason I lost a parentheses or something. Yeah, not there. Okay, so it looks like I'm getting, how far do I need to go? So there's one, first one, this is 1.05. Oh geez, I need to go all the way to 1.5. So I'm thinking it's 1.2696. Oh, where is it? Can't find my homework. Did I cross it out? Where's my homework? Yeah, 1.2696 with h is 0.05. It's right here. Okay. Or if I want 0.1, I can just go up here to my h value and make that 0.1, and then run it again. And 1.2194 is right there. Okay, so you just have to give me those two answers, and put that on a piece of paper. That'll be with your 2.4. So 2.4, this is like your quiz, homework number 3. And 2.6 is just number 5 from, so y of 1.5. Okay, I'm just copying it down so I have it in my notes. As usual, thank you. So all you have to do is write down those two answers for this video. Okay, as usual, thank you for watching, and I will see you next time.